All right, this is a video for geometry on midsegments of triangles, some of the properties associated with them, and we will start off with an introduction and then do a few solved examples. So I want to remind you first about what a midsegment is. A midsegment is a segment connecting the midpoints of two sides of a triangle. Okay, so a midsegment does not intersect a vertex of a triangle. It always goes between the midpoints of two sides. So I'm showing you a midsegment right there. Okay, there's a pretty useful theorem that we're going to work with called the triangle midsegment theorem, and it gives us two things here. So if we have a triangle with a midsegment, okay, so if we know that we're working with a midsegment, it gets us two things. One thing that it gets us, and I'm going to actually erase the givens here so to be clear about what's given and what's concluding. One thing it gets us is that these two sides are, or these two segments are parallel. So the midsegment will always be parallel to the third side of the triangle that it doesn't intersect. The other thing that is really quite useful is this midsegment has a length that's half the distance of that third side. Okay, so two quite useful results here. The midsegment is parallel to the third side and half the length of the third side. So let's do a couple practice problems using that theorem. First, I have a triangle with three midsegments actually all drawn in, and we know they're midsegments because we're being given these congruency marks. And our task is to just list out all possible segments that are parallel. Okay, and I'll try to color coordinate a little bit. Let's work with RT first. So RT is going to be parallel and half the distance, half the length of EF. So let's write that down. RT is parallel to EF. The other thing we can tell here, and I'm not going to do this for each of the combinations we're working with, but we can also conclude that RT, being half the distance, half the length of EF, has to have the same measure or the same length as SF or ES. So we could also say that RT is congruent to, I'll say SF, okay? So that's one possibility, and those are the ones, I'm going to kind of highlight those in red. And let's do one more. There are three midsegments, so you could do this 3 times over, but we'll do it once more with a different color. Let's look at RS and DF, okay? So we can conclude that RS is parallel to DF. And we can also conclude that line segment RS is congruent to half of line segment DF. So that would be, say, DT or TF. Okay, so those are a couple examples right there of some of the things that you can get using midsegments. Next one we'll do is we'll look more specifically at finding lengths. And again, this has a lot going on, and we can do a lot with it. I won't clutter it up too much, but let's actually just write in the picture rather than writing it by the side. So first thing I hope you can see is that these are all midsegments. We have UT and B are all midpoints of the corresponding sides of their triangles, of the triangle. So we can tell right away, I think, that this has to be 25 and 25, right? That's what T is a midpoint, so it splits that 50 into two 25s. And similarly, with the right-hand edge of the triangle, we have a couple 20s, okay, being half of 40. Let's, again, try to color coordinate a little bit here. So let's think about those two pieces. So UB has to be half the length of QS. 's. So that would make this 25. And similarly, UT needs to be half the length of RS, so that would make this 20. Lastly, we can think about the top side QR and how it relates to segment TB, midsegment TB. And I hope you can tell that QR would be double the length of TB. So QR as a whole will be 60. And each of the pieces of QR, QU and then UR, would each be 30. Okay, so just that one simple theorem gets us so many results. It gets us a lot of pieces of triangles, a lot of lengths for not too much effort. Our last one we'll do for this video is a real world problem, and this is, I hope you can imagine something that really is a real world. It's not just, I'm not just making it up as a possible real world problem. It's something that a surveyor would actually do. So the scenario is we want to find the distance across this lake, okay, from B to A. What's the distance across that lake? You don't have access to a boat. You're not going to wade the lake or swim the lake. But you have plenty of measuring devices and measuring tapes and such on the shore. So what can you do? Well, you can find a point E that's where you could draw a line to A and to B without actually entering the water. Okay, so you find a point E off to the left somewhere where you could draw line segment EA and then line segment EB. And then you're just going to find the halfway point, the mid-segment of the triangle, the midpoints of those sides you just created. And once you know that you have a midpoint set up, and so that midpoint would be midpoint D connecting to midpoint C would give us a mid-segment. So we can therefore just conclude that BA has a length of 92 feet. And that would be a pretty accurate, pretty precise measurement across the lake, 92 feet. So certainly a real world example of using the mid-segment theorem, and that's a great place to stop right there.